Have you ever looked at someone's braces and just seen, a bunch of metal? Well, get ready to see them in a completely new light, because what looks pretty simple is actually a marvel of biomechanical engineering. It's this finely tuned system, and it's all designed to solve one really fascinating puzzle. Let's get into it.
So this is the big question, right? I mean, it sounds almost impossible. Our teeth are anchored into our jawbone for a reason. They're built to handle massive forces when we chew. So how in the world does an orthodontist convince them to just march into a perfect line without causing all sorts of damage? Well, the answer is all about mastering force.
And this is the golden rule. It's the guiding principle behind all of modern orthodontics. You don't want a big, powerful shove. You want a gentle, persistent nudge. Everything, and I mean everything about braces, is designed around delivering this exact kind of force. And to do that, you need some very, very special tools.
Okay, so let's build out our toolkit, and we're going to start with the absolute heart of the system, the arch wire. To really get why certain wires are used, we've got to talk about three key properties that engineers and orthodontists are completely obsessed with. First up is strength. This one's pretty straightforward, right? You need a wire that's strong enough to keep its shape. If the patient bites into a crunchy apple and the wire permanently bends, well, game over. It stops applying the right force and the whole system just fails. Next is stiffness, and this is all about the force level. Now, you might think a stiffer wire is better, more powerful, right? But actually, no. A really stiff wire delivers this huge initial force that just drops off a cliff the second the tooth moves a little. And remember that golden rule? We want a light force. So a wire that's too stiff is a big problem. We need something a bit more flexible.
And that brings us perfectly to range. Think of this as the wire's memory. It's how far you can bend it, and it'll still remember its original shape and spring right back. A wire with a high range is amazing because you can tie it to a super crooked tooth, and it'll just keep applying that gentle, continuous force for a long, long time as the tooth moves into place. It's incredibly efficient.
So here's the bottom line. We're looking for what you could call a Goldilocks wire. It needs high strength, so it doesn't get messed up. It needs low stiffness, so the force stays gentle. And it needs a high range, so it can work for a long time. But you see that little formula on the slide? These properties are all connected. You can't just change one without affecting the others. For decades, this was a huge engineering headache, until a truly revolutionary material came along.
This material just completely changed the game. And, like so many modern marvels, GPS, memory foam, you name it, it actually has its roots in the aerospace industry.
So for a long time, orthodontists were using gold alloys. Then, in the 50s, stainless steel became the standard. And steel is great. It's strong, it's cheap, but it's also really stiff, which, as we know now, isn't ideal. Then, in the 1970s, this alloy that was developed for the US space program, called nitinol, found its way into orthodontics. And this nickel titanium, or niti, had a property that seemed, well, almost like magic.
That property is called superelasticity. And we're not just talking about being a little springy. This is on a whole other level. A niti wire can be bent and twisted to an incredible degree and still snap back perfectly to its original shape. And the reason why is so cool. When you stress the wire, its internal crystal structure literally transforms into a different phase. And when you let go, it transforms back. This reversible shift at the molecular level is what gives it that unbelievable range.
And wow, this slide just illustrates the difference perfectly. Look at the stainless steel wire on the left. It starts with this big, high force that just plummets as the tooth moves. That is not the light, continuous force we're looking for. Now look at the super elastic niti wire. It's this beautiful, low, almost perfectly flat line. It's a force plateau that stays constant across a huge range of movement. It is literally the perfect tool for the job. Okay, so we've got our revolutionary material. Awesome. But having the perfect wire is really only half the battle. Now you have to use it to control exactly how the tooth moves with absolute precision. And for that, we need to talk a little physics.
Don't worry, this isn't going to be a huge exam. There are just three key ideas. A force, that's easy, a simple push or pull. A moment is that tipping or rotational effect you get when you push on something off-center. And a couple, that's a pair of forces that creates pure rotation without any pushing. The best example is turning a steering wheel with two hands. Mastering how these three play together is the secret to orthodontic control. So this brings us to our next big engineering puzzle. Think about it. If you just push on the top of a tooth, the crown, its natural pivot point, or center of resistance, is way down in the root. So what happens? It tips over.
The crown goes one way, the root goes the other. So how do you get the entire tooth, root and all, to slide sideways perfectly straight?
The answer is this absolutely brilliant concept of balancing forces. The wire pushing on the bracket naturally creates a tipping force, a moment. But by using a rectangular wire inside a rectangular slot, orthodontists can also create a counter-tipping force, a couple. And by precisely controlling the balance between these two, the tipping and the counter-tipping, they can literally dial in the exact kind of movement they want.
So let's look at the options. First, if you have zero counter-tipping force, you get exactly what you'd expect, uncontrolled tipping. This is the default movement. The crown moves one way, and the tip of the root actually moves the opposite way.
Now here's where the real magic happens. If you can engineer the system so that the counter-tipping force perfectly balances the natural tipping force, if that ratio is exactly 1, you get pure bodily movement. It's also called translation. The tooth just slides perfectly sideways, root and crown moving together as one unit. This is a true feat of precision engineering.
But you can even take it a step further, which is just incredible. What if you make the counter-tipping force even stronger than the tipping force? Well, something amazing happens. The root of the tooth actually moves more than the crown. This is called torque, and it's how orthodontists get that fine control over the final angle of the root deep inside the jawbone. All right, we've talked about the amazing wire, and we've talked about the physics of moving a single tooth, but there is one more crucial piece of the puzzle we have to cover. When you start pulling on one tooth, how do you keep all the other teeth from moving? This is the science of anchorage.
It all comes down to pure Newton, right? For every action, there's an equal and opposite reaction. So if you use your back molars to pull your front teeth back, well, those same forces are also pulling your molars forward. The whole challenge is making sure that only the teeth you want to move are the ones that actually do.
One really common and clever strategy is to just break the movement down into steps. So instead of trying to pull, say, 6 front teeth back all at once, you might first pull just the strong canine tooth back by itself, pitting it against the resistance of all the other teeth combined. Then, once that canine is in its new home, it becomes part of the anchor team, making the anchor even stronger for step 2, pulling back the front 4 teeth. It's a brilliant divide-and-conquer approach.
As we start to wrap this up, I really want to leave you with a sense of the incredible scale and precision we've been talking about. This is not a world of brute force at all. It's a science of microns and grams.
Just get a load of this. To achieve that perfect straight-line movement with a gentle net moving force of just 50 grams, the wire has to create a powerful counter-tipping force inside that tiny little bracket slut. And that force can be over 1,100 grams. That's almost 2.5 pounds. All of that is happening inside a tiny component just a few millimeters wide. It's a staggering amount of force, all perfectly balanced and completely under control.
So the next time you see a smile that's been perfected by orthodontics, I hope you remember what you're really looking at. It's not just straightened teeth. It is the result of a super elastic alloy born from the space race, the precise application of forces and couples, and this deep, deep understanding of physics and biology. It's just a reminder that some of the most incredible engineering is hiding in plain sight. It kind of makes you wonder, right? What other marvels are right there in front of us, just waiting to be explained?